Good afternoon. My name is Russ Klein. I'm a technical director with Mentor Graphics, now a Siemens company. I'm going to be talking today about accelerating inferencing on embedded systems with RISC-V. So what we find today is that in the machine learning space, inferencing algorithms are particularly compute intensive, and they generally are exceeding the performance capabilities of embedded processors. There are exceptions, of course, but that's the general rule. So I'm going to go through a description of an exercise that we went through to create both a coprocessor on the Rocket core, the Rocket core going through the Rocket core coprocessor interface, as well as creating a bus-based peripheral. Now, when we set out on this project, we wanted to also look at extending the instruction set to make inferencing algorithms go faster. And what we were playing with, we found out, just wasn't a really good fit for these algorithms, trying to extend the instruction set. Although at this conference, I've actually learned some really good ideas around that. We may go back and try things. But as we were approaching the problem, it really was contorting it way beyond what you'd normally want to do in an instruction. So we'll really be talking about both the coprocessor and the bus-based peripheral. Now, everybody who talks about inferencing in embedded systems has to have a slide on automated driving. This is one of the most computationally demanding applications that's out there. Right now, cars are not fully self-driving, and they typically will have about 6 cameras in them at 30 frames per second. What I want you to remember from this slide is that's more than 1 billion pixels per second that the car needs to process. And the number of cameras is going up, and the resolution is increasing, so that problem's going to get harder. But not all embedded systems are created equally. So this is a Ring doorbell. I have one of these in my house. And it does some heuristics to figure out, is there a person out there or not? And the heuristics aren't really very good. At 4 a.m., if the neighbor's cat walks across the railing on my front porch, it wakes me up saying there's a person out there, which is irritating. Now, I know somebody's created some AI that can identify cats in videos. So if they could apply that to this, it wouldn't have to do 30 frames per second. It could do a frame every 1 or 2 seconds and decide, nope, that's a cat. Let's let them sleep in. And that would be processing well under 1 million pixels per second. So we've got 4 orders of magnitude between these 2 different examples. If we look at the total spread on embedded systems that need to do inferencing, it's probably much closer to 5 orders of magnitude, from the most demanding to the least demanding. And this means that there's not going to be one application that's going to work great for every single thing. As such, we're going to walk through an example of sort of building your own accelerator from source code. And the algorithm that we're going to use to go through this is called Yolo-Tiny, and this is Yolo-Tiny version 3 specifically that we worked on. And this is an algorithm for detecting and classifying objects and pictures. It's typically used on cell phones or computationally limited devices. There's a total of about 5.5 billion floating point operations that it needs to do per inference, with over 36 million weights and biases that it brings in. The neural network has 23 layers, and if we contrast this with the full YOLO, that has 106 layers and handles about 8 times as much data. So what we're looking at here is a fairly constrained neural network. And if we run it and turn on the instrumentation in the Yolo-Tiny, we get an output that looks something like this. It tells us what each layer was, and then what the computational load was. And what you notice here is that there's a 3x3 convolution followed by a 2x2 max pool over and over again. There's 6 of those in a row. And then another 3x3 max pool that has the, or 3x3 convolution that has the 1.5 billion operations, and then another 3x3 that has about 1.1 billion operations. So if we had an accelerator that did a 3x3 convolution followed by an optional 2x2 max pooling, this would speed up over 96% of that total lifting in that algorithm. And so that would give us the ability to speed things up rather dramatically. Now, what's a convolution? This is the absolute best diagram I've ever seen of a convolution. I got it from embeddedvision.com. And essentially, this is the image. It's an array of numbers. And this bit right here is our convolution kernel, or our filter. You'll also hear these referred to as weights. And what we're going to do is take each element in a 3x3 region in the source image and multiply it element-wise with each element of this 3x3 array. And then we're going to sum those values up, and that becomes our output value. So that's a 3x3 convolution. They're pretty simple, but just so everybody knows what we're going to be doing here with the math. Now, we're going to be doing a 3x3 convolution followed by a 2x2 max pooling operation. And so what we're going to do is take a 4x4 matrix in our original image, and we're going to do 4 3x3 convolutions, which we're going to put into this 2x2 array. So if we do this 3x3 area multiplied by that kernel and sum them up, we get 681. And then we can move over to the right, and then down and to the left, and then to the right, and we've computed our 4 output values. Now, if we're not doing the max pooling, we return those 4 values. Those go into the resulting image. If we are doing the max pooling, we take just the largest of those 4 numbers. That's all we need to do. It's just a maximum of the 4 numbers and return that. And we repeat that, so we're going to take this rectangle, move it over 2 pixels, and then repeat the operation across all 4 of those, and then repeat that for the entire image. So some observations at this point. The 416 by 416 pixel image that we're reading in, that's what Yolo-Tiny is designed to process, against a 3x3 convolution, that's 1.5 million multiplications. Now, this is an embarrassingly parallel application. So we could do all of those multiplies all at once. If you could get that many multipliers on a piece of silicon, and if you could get the data to and from those multipliers, which becomes a real challenge. And this is only 0.002% of the entire multiplies that we're going to do for the entire inference. So we've still got quite a bit of work to do after this one. So we're going to create our accelerator using high-level synthesis. High-level synthesis is a technology that's been around for years. Many of the EDA companies offer it as a product, and there are a number of open source tools that do the same thing. Fundamentally, high-level synthesis is going to allow you to operate more abstractly. We can write an algorithm in C or C++, and then use this synthesis tool to create synthesizable RTL. So it's going to handle a lot of the low-level details that you probably don't want to bother with. And once what it's going to do is compile up that C code and create a control data flow graph that represents the algorithm. And from there, based on settings that you give it, it can introduce parallelism, pipelining, resource sharing, and it can take large arrays and infer memories and then handle all of the interfacing for those memory devices. And it does this all automatically without you having to do a lot of work. And you might be thinking, well, I'm an RTL guy. I've done RTL for 10, 15, 20 years. I can do it just as well as I could write C. And you might be able to. But as you're going to see as we go through this exercise, you're going to write this algorithm once and you're going to realize, oh, that wasn't a great architecture. We're going to have to change it. And it's that changing it that becomes really challenging down at the RTL level and a lot easier at an algorithmic level. So let's go through this. The other benefit that you get from high-level synthesis is that it makes your verification easier. So the first thing that we observe is that we can instrument our original algorithm and get stimulus and results from when we run that. So you can just take that algorithm, you can run some images through it, capture what went in, capture what went out. This can become your test bench. Also, the original C++ can be inserted like this and become an oracle for your design in the test environment. So when we go down to RTL, we can give the same stimulus to the RTL, the original algorithm, and see that we get the same answer. But there's another thing we can do with this. If we link in our high-level synthesis tool with our formal verification, that controlled data flow graph that we created can be then used as a formal comparison against the RTL. Now, we may not be able to mathematically prove that the RTL and the original algorithm were equal, but we can eliminate a lot of the state space that we need to search through in our verification. And this is going to reduce our verification needs pretty dramatically. We actually do have a customer who went through this with these tools. It's NVIDIA, and they were building the Xavier chip. There was part of that chip that was done with high-level synthesis. Traditional RTL functional regression would have taken about 3,000 CPU months. Using these formal properties and the high-level synthesis, they were able to achieve the same thing in 2 weeks with 7 CPUs, or 7 CPU months. So that's a total of a factor of 500 in the compute resources needed. And they reported that they got an 80% reduction in the manpower necessary to do that. So pretty big savings there. So this Yolo-Tiny algorithm, if we had a database of 1,000 images that we wanted to crank through it, on my MacBook Pro, it takes about 1.5 seconds per inference, or that's about 25 minutes to do a complete regression. If we take our behavioral C implementation, including all the overhead that we're introducing for interfacing and things like that, it would take us 5 seconds per inference, or about 1.5 hours. If we did that same verification against the implemented RTL, we're looking at 389 minutes per inference, and that's about 9 months. So a very significant savings if we can do the verification at the behavioral level and then prove that the RTL is equivalent. That's a significant savings there. So this is the implementation that I put together of the 3x3 convolution and 2x2 max pooling. So this outer loop just goes over the input image, and then we've got an inner loop that goes through the 4 regions that we're going to collect the convolutions from. And then the next inner loops are step over the convolutions themselves, and then we perform the multiplication here and sum them up. If we're doing a max pooling, we want to take the largest of them, and if we're not doing a max pooling, as we compute each sum, we just put it into the output. And so with the high-level synthesis, we can take that algorithm as we described it without any other changes, and we can create a number of different implementations. So we can create a single multiplier and have it take 84 clocks, 36 multipliers, and we'd have a total of latency of 3 clocks, or we could do 216 multipliers, and we get 2 answers every clock cycle. So based upon what our needs are, how much area we want to take up, how much power we want to consume, we can just pick an interesting point on this array, and we could go further down and just bulk it up. This is a schematic that was output from a 36 multiplier selection, where we basically just do all 36 multiplies in a single clock. The other thing we can do with high-level synthesis is we can do operation sizing. So fixed point arithmetic versus floating point arithmetic at the RTL level is significantly less expensive. But we don't need to leave things at 32 bits. We can actually reduce the number of bits in our fixed precision numbers. We actually observed that the Yolo-Tiny, as we went from 32-bit floating point to 20-bit fixed point, it actually increased in accuracy. It got more accurate. And this is consistent with what folks have found on quantizing numbers that are going into machine learning algorithms. We do have a library of fixed point types that's available as open source, and it's at hlslibes.org. And these can then be run in the algorithm on the desktop, and you can look at your accuracy with different levels of precision. Also, the multiplier costs in terms of area and power is roughly proportional to the square of the operands. So if we can go from a 32-bit fixed point to a 12-bit fixed point, we're going to use about 1/7 the power. So this can be a really significant power savings. So we ran it through the synthesis tool. We built an accelerator, and we did the 36 parallel multipliers. And then we put that into a rocket chip tile. So this is the rocket core. It's connected to an L1 instruction and data instance. So the accelerator has a path directly to the rocket core and one to the L1 cache. The interface that comes out as we synthesize it is a ready valid data combination, which works very well with the protocols that are exposed on the RISC core, on the rocket core. And then we program it using the custom 0 instruction, which is the send to coprocessor instruction. We didn't make an update to the compiler, the tools. We could have, it's just some overhead, and we weren't doing anything fancy with the instructions. And so we accessed the kernel and image data. It was going through this L1 data port. So details on the RoCC chip coprocessor interface. If we had more time, I'd go into these details here. But if you want to know the details, Colin Schmidt in a 2015 RoCC chip tutorial bootcamp did a great explanation of it, along with course notes from CS250 at Berkeley and some GitHub examples. Colin is actually here at the show today. I don't know if you're out there, big thank you, because your work made this a whole lot easier for us. So putting in this accelerator was really straightforward. So what we found is that the software was executing one multiply in every 7 instructions. And we found this by examining the optimized output of the compiler. And the accelerator was executing the 36 parallel multiplies in one clock. And then we had 2 more clocks for the adder tree and then the comparator. So our accelerator was about 100 times faster than the software, which is about what we were expecting to get. So 3 clocks versus 7 clocks times the 36 multiplies plus some overhead, about 3 versus 300. So a very nice speed up. We were doing high fives in the hallway and around the cubicles. And then one of our team members said, wait, but if you take the 3 multipliers and we look at how many clocks that's taking and we add up the total amount of algorithm, it's 4 times too slow. And we looked at it and said, hey, you're right. And so then we had to figure out, why did we lose 4x in terms of performance? And what we did was looked at the bus. It was almost 100% utilized. We had really nice burst cycles from where the image was. Everything was looking great. And then we looked at the cache misses. And we turned out we were hitting lots and lots of cache misses. So what's going on? So remember, we were looking at this 4x4 region. And once we processed this 4x4, we were going to delete the leading 2 words and then add 2 words on each line to fill out that next 4x4 region. Well, all of the pixels that we just read in are all on different cache lines. And because they're all on different cache lines, we get a cache miss on every single one. Anything the processor does causes additional cache misses. And so we were just thrashing the cache, and that was giving us about 1/4 of the performance that we expected. So what do we do about it? What we did was created a shift register that was 3 lines long plus 4 pixels. And so then we would have all this data in the accelerator to process the algorithm, and then we could just go get 2 more words, and we'd have enough data to compute the next one and repeat. And so this made our caches much happier, and it actually quadrupled the performance of that accelerator. When we tried to do this as a complete shift register, there's 1,260 registers that we'd need to create that in a total shift register times 16 bits that we were using for the width of the weights, which is about 20,000 bits in a shift register. And that thing's going to get hammered every single clock. And that was going to take up a lot of area and use a lot of power. So what we ended up doing was having 4 word shift registers where we had taps in for the multipliers, and in between them we had memory with circular buffers. And this made for a much more power and area efficient implementation, but still gave us the very nice implementation with respect to the caches. So an alternative to programming it up as an accelerator that lives in the RoCC core tile is to put it out on the bus. And in this case, that worked out fairly nicely for us because we found that between what the RoCC core was doing and what the accelerator was doing, they were sharing that L1 data cache. This connection to the bus became a bottleneck, and that was actually slowing us down. Putting it out as a peripheral accelerator eliminated that. So we're no longer talking to it through the instructions, but we now had a memory mapped control interface that sat down here. Again, we've got ready valid data connection point here, so it's fairly easy to tie into either TileLink or AXI. And the accelerator would master to go out and get the kernel and data image. As we did this, we looked at, there was a lot of data moving. And one of the things, this was from an NVIDIA DAC paper that talks about the relative cost of the different operations that you'll do in an inference. And what they found is that going out to DRAM is roughly 200 times more expensive than doing an ALU operation. So one of the things that you want to make sure you do is move as little data as possible. So what we found is we profiled the Yolo-Tiny. I know this is a bit of an eye chart, but I want to point out one thing. When we start off early in the algorithm, the first 4 layers, the coefficients are really pretty small. We've only got a few of them. And when we look at the feature size toward the end of this, the feature size become much more tractable. They're smaller. They're not small, but they're smallish. So for the first 4 layers, we would bring in a feature and then a coefficient. We'd keep the architecture that we described so far. But for the later layers, what we did was reorganized so that instead of the kernels being processed for each frame, we'd pull in a kernel and then process a bunch of feature data. Now, this doesn't seem like it'd have a really big impact. We're just changing the order. But fundamentally what it does is it allows us to take all of the features and put them in a feature memory. And we'll bring in one kernel and we'll run all the features against it through the multiply accumulate engine and store the results in memory B. Once we've got it in memory B, rather than moving it back up to memory A and doing the next kernel, we actually just mux the memory so that the feature data, which was processed by the kernel, could now be sent the other direction, processed by the next kernel. And so this eliminated a lot of data movement, and likewise the time and the energy associated with that data movement. The final thing that we wanted to look out for was the organization in memory. So within each of these feature maps, when we're convolving it against a kernel, we need to grab this data point 1, 5, 9, and 13. And if they're all in separate places in memory, we have that same problem that we had with the caches where those aren't lined up and we need to access them differently. So this was solved by simply reordering how they were in that feature memory. And so if we ordered them the right way, we could pull in multiple words with a single read from memory and apply it into the convolution algorithm. So in conclusion, we built an accelerator for a 3x3 convolution and 2x2 max pooling. This was a total of 96% of the load for this object recognition algorithm. We built it with 36 parallel multipliers and then pipelined an adder tree and comparator on the tail end. This was implemented both as a rocket chip coprocessor and a bus-based peripheral. The rocket chip accelerator is going to work well if your algorithm is sharing state with the software, and so they take advantage of a common cache. In our case, in this example, it wasn't the case. So having an independent bus interface was a better choice because we were communication bound. We were limited by how fast we could process, by how quickly we could bring the data in. And going through this, we used high-level synthesis, which allowed us to create an accelerator that was very specifically customized for this application. It had the exact number of multipliers that we wanted. It had the bit width exactly that we wanted. It had the data paths through it that we specifically wanted. High-level synthesis will allow you to accommodate those last-minute changes because these algorithms do change. A new algorithm comes in, and you need to be able to adapt to it. And you can go from that algorithm to the RTL very quickly. And this RTL could be targeted to ASICs, to embedded FPGAs, or traditional FPGAs.